All right, so for problem number 1, it says a bag contains 6 red, 4 blue, and 8 green marbles. I want to know how many marbles of each color should be added into the bag so that I now have a total of 27, but the probabilities of each color still remain the same. So I don't want the probabilities to change. All I want to do is add additional marbles into the bag. So who thinks they can tell me how many red might need to be added into the bag? Not new, not how many new red is there going to be, is how many are we going to add? What additional amount do you think? Abby? 3 red. Very good. How many blue? Elisa? 3. Not 3 blue. Trey? 2. 2 blue. And then how many green should we add in? Eileen? 4. Okay, so it looks like your table got it all together. So let's go over how you would do that. So the first thing that we need to know is what are the probabilities of each of the colors. So I know that the probability for red is going to be 6 out of 18. So currently my probability for red is 6 out of 18. I'm going to simplify that. I want to put it in simplest form. That would be 1 over 3. You could use your calculator to do that. Okay, I'm going to do the same thing for the blue. I know the probability for blue is 4 out of the 18, which in its simplest form is going to come out to 2/9. And then the probability for the green is going to be 8 out of 18, which would simplify down to 4/9. So those are the probabilities that I'm currently working with. I want those probabilities to remain unchanged in their equivalent form, but instead of having 18 as the total, I now want 27 as the total. So this is something that you guys learned back in 6th grade with ratios and proportions. That if you want an equivalent ratio, you just need to figure out how much out of the new total. So what should it now become out of 27? What should it now become out of 27 for all of them? So it's setting it up as a ratio or a proportion. Once I have it as a proportion, I can do a cross product to solve. So this is going to be 3 times x. And this is going to be 1 times 27, which is 27. And then if I go ahead and divide both sides by 3 like we learned last week with our one-step equations, then I would get down that x has to be equal to 9. So that means that 9 red out of 27 would be equivalent to 6 out of 18. But 9's not my answer. 9 is how many are the red going to become. Okay, it's going to go from 6 to 9. So what was that an increase by? An increase of 3. So we need to increase by 3 red. Because we're going from 6 reds to 9 reds in order for the probabilities to be the same. 9 over 27 is the same thing as 6 over 18. They both simplify to 1/3. Okay, doing the same thing for my blue. 9 times x gives me 9x. 2 times 27 gives me 54. I need to solve by dividing both sides by 9. And here, instead of having 4 blue, I now need to have 6 blue. So that means that blue had to increase by 2. To go from 4 to 6, it's an increase by 2 blue. Okay, then our last one. We're going to cross product. 9 times x is 9x. 4 times 27 is going to be 108. Divide both sides by 9. and we'll get that we now want to have 12 green. So we're going from 8 green to 12 green. That's an increase of 4. Any questions on that first one? Okay, all we did was create equivalent ratios, equivalent probabilities, and identify what we had to increase by to get to those equivalents. Okay? Yes? So this x was just showing us what the new value would have to become. So instead of 6 out of 18, it's 9 out of 27. 9 over 27 simplifies to 1/3. 6 over 18 simplifies to 1/3. So that means we need 9 red out of 27 total marbles. Okay, that x just tells you what the new value is going to be, but they didn't want to know what the new value was. They wanted to know what you would increase by. Okay? All right, problem number 2. For problem number 2, we have 20 red Skittles that are mixed in a bag with an unknown amount of green. So we have red and green Skittles all mixed together. 20 Skittles are red. We don't know how many are green. We're going to pull 15 Skittles out of the bag. And from that 15, we know 5 of those are red. So the rest would have to be green. And based off of that, what can we assume would be green's original total in the bag? So we're making an assumption. This is going to be using predictions. Again, we're going to be using a proportion to work that out. We're going to use a proportion to work that out. So we know that we pulled out 5 red marbles, which means we pulled out how many green? 10, right? If 5 were red, then the remainder had to be green. So 15 minus 5 gives us 10. So 10 green were pulled out of the bag. So I can put that down, that I pulled out 5 red and 10 green. So all I did was make a ratio, comparing my red to green from the bag that I pulled out, from what I removed. So this is information I know, exactly, I know all this. Now here's partial information I know. I also know originally, so here, I'll write this out on the side. This is what we pulled, and this one's going to be what was originally. So originally in the bag, how many were red? 20. Originally in the bag, how many are green? We don't know. That is an unknown. It's an unknown amount of green. So when it's unknown, you put X. So 5 red, 10 green were pooled. 20 red, an unknown amount of green, were originally in the bag. We've now created a proportion. We can use the cross product to solve. So we're going to multiply 5 times x, which would give us 5x. We can multiply 20 times 10, which would give us 200. And then we would just divide both sides by 5. And we would find out that x is going to come out to 40 green. So originally in the bag, we can assume that there's 40 green, if it happens to be proportional. It might be a little bit more, it might be a little bit less, we don't know. But based off of the results, we're making an assumption. All right, number 3. What is the probability of selecting a vowel from the statement Axio homework? If you ever, read Harry Potter, that's the summoning spell when they want homework to be brought to them or something. Okay? So a vowel, A-E-I-O-U. A-E-I-O-U. Okay, those are our vowels. So we've got A, I, O, another O, E, and another O. How many vowels did I highlight? 6. I highlighted 6. So the number of vowels that I highlighted were 6. And then how many total letters are in the statement here? 15. No, not 15. 13. 13, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 letters. So 6 out of 13. Cannot be simplified. If you plug it into your calculator and hit enter, it will still come out as 6 over 13. It's as simplified as it gets. It's a nice and easy one for you. Okay, last problem. For experimental to be as close as possible to theoretical, what did we say has to occur, Cheyenne? A large number of trials. You must have a large number of trials. That's important. The more trials you have, the more accurate your results will be in comparison to the theoretical. Are there any questions about this warm-up? Okay, let's get into the notes then. If you could go ahead and turn your page to page 7 in your notebook. If you didn't get all of this down, it's fine. It'll be on Google Classroom tonight, okay? But we got to get moving. Or you can borrow my notebook later. So we are on page 7. Don't forget to number your notebook, page 7. And we're going to be talking about tree diagrams and compound events today. Tree diagrams and compound events. So a tree diagram, you guys have seen tree diagrams before. You've seen different formats of diagrams like Venn diagrams. A tree diagram is just an organized way to display a list of possible outcomes for multiple events that are happening or multiple activities. So it's an organized diagram. Used to represent what we call a sample space. It's just a list of all possible outcomes. So it's a, oops, I even wrote list. It's a sample space of all possible outcomes for what we call compound events. Compound events means there's more than one activity. So it's not just a coin. You might have a coin and a spinner, or a coin and a die, or maybe all three. Okay? And we talked about it last week that you experience compound events all the time. Using that fundamental counting principle, we were able to identify how many different combinations you could create for lunch. Okay, so let's take a look back at that example, our lunch choice example. So before we found out that there were 18 different outcomes that we could create, let's go ahead and see what that sample space would actually look like. So we said before that you could have a choice of milk or water, that you could have a choice of a sandwich, pasta, or chicken. That was your entree choices. And that you could also have a choice of salad, soup, or fruit as a side. So now for a tree diagram, creating a sample space, it's the basic idea of a tree. You've got the main base, right? The trunk, what builds the trunk. Then you've got the branches that extend from the trunk. Then you've got twigs that might extend from those branches. Okay, so it's building this set of different outcomes that can be combined together. So we're going to look at our first activity. Our first activity is displaying our drink choice. So for our drink choice, we have two possible outcomes. We can have milk, and I'm just going to put M to represent milk. Or we could have water. I'm going to put W to represent water. Okay, so those are my two possible outcomes for a drink choice. I've now built my main base, my trunk of the tree. That's the beginning of the tree. From there, I can then extend out to create my branches, which is my next activity. After I choose my drink, I go choose my main entree, my main course. So if I choose milk, I have three possible outcomes for a entree. I have a sandwich. I'm going to make that S a little bit bigger. I have a sandwich. I have pasta. I have chicken. Okay, but the same thing with my milk. When I choose milk, I also have three entrees that I can choose from. I have the sandwich. I have the pasta. And I have the chicken. Okay, so I have my trunk. I have some branches. But I'm not done. I still have side choices that can be chosen. That's going to make my little twigs. That makes the twigs of the tree. So from there, how many twigs do I have? 1, 2, 3. From each one of these, I now have 3 twigs. I can have salad, I'll put S-A. I could have soup, S-O. Or I could have fruit, F. And I'm going to do that from each one of these choices. Salad, soup, fruit. Salad, soup, fruit. Okay, and I keep doing that for every one of these. Those are my small little twigs that are coming out of the branches. Okay, and it's a lot, but it allows me to see what my sample space would be. So my sample space dictates what every single possible outcome is. Okay, so my first possible outcome is choosing milk with a sandwich and a salad. Notice that I'm just following my branches up. So milk, sandwich, salad. Now, because I'm done with that choice, I'm going to go ahead and put a check mark by it so I know not to choose it again. Second one is milk. I can still go with sandwich because I still have more options. Soup. So milk, sandwich, soup. I'm done with that one. I still have one more with the milk sandwich variety. Milk, sandwich, and fruit. Milk, sandwich, fruit. Now, I finished all 3 of these twigs, which means that this branch of sandwich is done. I'm going to go ahead and put a check mark by it. Does that mean milk is done? No, because milk still has some other options, doesn't it? I still have milk and pasta. So now I'm going to go ahead and relay all of those options. I've got milk, pasta, and salad, milk, pasta, and soup, milk, pasta, and fruit. So I've got all the milk pasta combinations. Pasta's done. Is milk done now? No, why not? I still got chicken. So now I'm going to come and do all the milk and chicken combinations. I've got milk, chicken, and salad, milk, chicken, and soup, milk, chicken, and fruit. So now chicken's done. Is milk done now? Yes. Milk is done because I've done all the milk sandwich, the pasta, and the chicken combinations. Milk is done. Now I go down to the rest of my tree, the water portion. And it's just going to repeat exactly like this was, but instead of milk, it's all going to be water. So we've got water, sandwich, salad, water, sandwich, soup, water, sandwich, and fruit. So those three are done. So sandwich is done. Then I've got water, pasta, salad, water, pasta, soup, water, pasta, fruit. Pasta is done. Water, chicken, salad. Water, chicken, soup. And water, chicken, and fruit. Chicken's done, so now water is done. So the whole thing is complete. This is my sample space. How many outcomes are in my sample space? 18, which is what we had found before with fundamental counting principle, that we took 2 drinks, multiplied it by 3 entrees, and multiplied it by 3 sides. 2 times 3 times 3 gave us 18. So the fundamental counting principle tells you how much should be in your sample space. The tree diagram depicts what each specific outcome looks like, which is helpful because sometimes you might need that visual, especially if I ask you, hey, what's the probability that you're going to choose a milk and chicken? I want the probability that I'm going to choose a lunch that's got milk and chicken in it. Has to have both, milk and chicken. Who can raise their hand and tell me which sample space items up here, which numbers satisfy milk and chicken? Just tell me which numbers. Trey? 7, 8, and 9. Those are the only ones that have both milk and chicken. Notice the word is and. That means it has to have both of those items in the sample space for it to satisfy. Now, if it said milk or chicken, that would be different. Milk or chicken means I could have milk, I could have chicken, I don't have to have both at the same time. So that would actually be items 1 through 9 and 16 through 18. So that would be 12 items instead of the 3. But in this case, it's 3. 3 out of 18, which simplifies to 1/6. It's helpful to have them written there and seeing what the sample space is so that you can identify the probabilities a little faster. Let's do another example. I'll tell you what, this is probably my least favorite part of probability, is doing the tree diagrams, because it's tedious. It really, really is, and I hate doing it too, but just feel good knowing that I'm here being tortured writing it just alongside you, okay? Again, these will be online. We don't want to waste too much time though, okay? This is page 8. Okay, we've got a coin and a spinner. I'll make this one smaller. A coin and a spinner. And the spinner's got 3 sections: pink, blue, and green. Pink, blue, and green. So those are my 3 sections on the spinner. Again, I want to create a tree diagram representing the sample space for these 2 activities. So we're going to start with the coin. This is my first activity. So I'm going to start with all the outcomes that go with the coin. What are the outcomes for a coin?
Heads and tails.
Heads and tails. So we're going to write a big old H and a big old T to represent heads and tails. There is the trunk of my tree. Now I move on to my second activity. My second activity is the spinner. How many outcomes are there for my spinner? 3. So each one of my coin outcomes should have 3 branches coming out of it, representing pink, blue, and green. Pink, blue, green. I don't have any more activities, so that is my tree diagram. My sample space is just depicting each of these. So my first possible outcome is to land on heads and pink. Then we could get heads, blue, heads, green. Then we could go to tails, pink, tails, blue, tails, green. There's my sample space. And again, if I wanted the probability to, I would land on heads, blue, heads, blue. How many outcomes are heads, blue? Philip?
I had a question.
Okay, question?
Like, what if the spinner was 1 pink and 2 blue? Would it still be the same tree but without the green?
No, because that would not be a uniform probability. This is more talking about mutually uniform probability, meaning that each outcome has an equal opportunity to happen. So that would be a different setting. Okay? Which you would still do it the same way. Like if this was 2 blues, you could still set it up and go, okay, well, the 2 blues is equivalent to, like, 1 pink is equivalent to a half of the blue, right? So they would still be equal size, so it would just be a blue and a blue. So instead you would have pink, blue, blue. That just means that you would have more of an opportunity of landing on heads blue than not landing on it, okay? All right, so for here, heads blue occurs only 1 time, right? Outcome number 2 is the only one that shows heads blue. That's 1 out of 6 outcomes. So there's your probability. Now, a tree diagram just models what it looks like. There is actually a faster way of doing so when you're talking about mutually uniformed probabilities. So we're going to talk about compound events. And again, we're going to do this as quickly as we can. Only a couple of examples. With compound events means it is 2 or more simple activities, like a coin and a spinner. Or, in this case, 3 coins. So if I have 3 coins that I'm going to flip, 3 coins are being flipped. I want to know what is the probability that all 3 of them are going to land on tails. So that means that I'm going to break this up into 3 probabilities. I have 3 activities. 3 activities are occurring. I'm going to split them apart. So I want the probability that the first is going to be tails. Then I want the probability that the second is going to be tails. And then the probability that the third is going to be tails. So what's the probability that the coin's going to land on tails?
On 1 coin?
On just 1 coin. 50-50, right? 1/2. So it doesn't matter whether it's 1 coin, 2 coins, 3 coins. Each individual coin has a probability of 1/2. Individually, they have a probability of 1/2. Now, together, because we have multiple events, you're going to multiply those probabilities to find out what the probability is of all 3 simultaneously occurring. So 1/2 times 1/2 times 1/2 is 1/8. So when it's compound events, all you're doing is finding the probability separately for each activity and then multiply those probabilities together. That's all. It's very simple, which makes sense up here. We take a look. The probability that the coin is going to land on heads is 1/2. And the probability that the spinner is going to land on blue is 1/3. And 1/2 times 1/3 is 1/6. So if you multiply your probabilities, you will find the probability of the total events combined together. Let's take a look at another one. Let's say that we have the die, and we've got this spinner. Okay, and the spinner is labeled A, B, C, D, and E. And what I want to know is what is the probability that the die is going to land on a number that is greater than 4 and that the spinner is going to land on a vowel. I want the die to land on a number greater than 4 and the spinner to land on a vowel. So what we do again is we take each of these activities and split them up. So instead of combining it, I'm going to look at them separately. The probability that the die is going to land on a number greater than 4. What is that going to be? So, not 1 out of 6. Greater than 4. So that could land on a 5. It could also land on a 6, can't it? Could it land on a 4? No. It has to be greater than 4, not equal to 4. So the only ones that satisfy it are a 5 and a 6. A 5 and a 6 are the only ones that satisfy it. That means you have 2 out of 6. 2 ways to get what you want. 2 ways out of 6 total numbers. You could simplify it now or you could simplify it at the end. It doesn't matter. Okay, then we're going to look at the probability that the spinner is going to land on a vowel. Remember, vowels are A, E, I, O, U. That means that the A and the E will satisfy what I want, which is 2 letters on that spinner out of 5. That's 2 letters out of 5. So then we're going to go ahead and multiply it. Again, if you multiply it in your calculator, it will spit it out simplified for you, which comes out to 2 out of 15. 2/15. Use those calculators. They are useful. They're there for a reason. I want you guys to try this one on your own. You've got a coin, a die.
Miss French-Zheng,
Yes. Yes.
I have somebody very special up here that's coming to your classroom, but I don't have anybody to bring her to you.
Okay, I'll send somebody.
Thank you.
Lisa, can you go get my daughter? She's at the front office. You know where the front office is?
Yeah.
Okay. Thank you. Shh. All right, so we have the coin, the die, and another spinner. A, B, C, D. A, B, C, D. Okay? Coin, die, spinner. And I want the probability that the coin is going to land on heads, the die is going to land on an even number, and that the spinner is going to land on a consonant. Go ahead and do this one on your own. Heads, even, consonant. Heads, even, consonant. Consonants are non-vowels. So all the letters that are not vowels. B, C, D, F, G, you know, so on and so forth. This is the last problem. Once you've done this problem, you've got your answer, go ahead and open up your laptops and log in to Google Classroom. I've got an IXL for you guys to work on. All right, who can raise their hand, tell me what they got. What's the probability? Abby? 3/16, correct. So probability for heads. Probability for heads is 1/2. The probability that the coin will land on an even number is 3 out of 6, or 1/2. And the probability that you're going to spin the spinner and land on a consonant is 3/4, right? There's 3 consonants out of 4 letters on the spinner. When you multiply them all together, that's going to give you 3 out of 16. 3 out of 16. Okay? Now, you guys have on Google Classroom, you've got your iExcel assignment. Again, make sure you log in. When you click on the link, log in with your username and password. Don't forget the @Northbrook MS. Needs to get to a SMART score of a 70.